Which one do you think's fastest? The one on top. Why do you think that's the fastest?
It's on a primary carbon, and that's the best for SN1, and it's iodine, so it's a heavy atom bonded to a light atom, so carbon iodine is a weak bond, so it will come off quicker.
All of that is right, except that the primary being the best for SN1.
Oh, it's not SN2.
Primary is best for SN2. So and actually this one's got a lot of bulk next to it, right? SN2 here, you're still looking at a lot of stuff next to it. But yeah, this one's primary. This one's tertiary. So if you think what has to happen, I guess rather than just writing that. So what happens if the leaving group leaves?
So the second one's
Yeah.
better now.
Yeah. So the slow step of SN1 and E1 is going to be the leaving group leaving, giving a cation. So you're essentially in an SN1, you're going to kind of rank by the cation that you get. I mean, that's going to be a lot of the thought process. And this is why I say this one's kind of hard. And we'll get to that in a minute. So anyway, yeah, iodide's the best leaving group on the board. Right, so we've got iodide, bromide, and OH. So iodide's the best leaving group, and it's on the one that gives a tertiary carbon. So the second reaction is the fastest. What's the slowest?
The bottom one,
How come?
OH is really bad leaving group.
Right, so OH is essentially not a leaving group. So even though you'd get to the same carbocation, to do that, hydroxide would have to come on. Which is this, if you want to think about it that way, right? We just did this on methanol. Right? If you see methanol as a solvent, you don't have a strong base because you're saying hydroxide can't leave. If you see a hydroxide in methanol, you're assuming hydroxide can leave. So hydroxide cannot leave like that, so that's going to be the slowest one. And like I said, so I just give this whole big, ranty, tangential discussion about only change a couple of things. Now you've changed two things. Comparing, so we know that the tertiary iodide should react faster than the tertiary bromide because iodide's a better leaving group. We know the tertiary iodide should react faster than the primary iodide because the tertiary cation is more stable than a primary cation. But comparing the tertiary bromide to the primary iodide, one's got a better leaving group, and one would make a better cation. So you're kind of guessing at that point.
Wouldn't a better cation be better?
It would. It would. It absolutely would. So your guess is good that the better cation, like again, the rate limiting step in SN1 is the leaving group leaving, and the thing that leaving groups, iodide, bromide leave just fine. The thing that's hard on them is the cation they leave behind. So that cation is the thing that's causing instability. I minus, Br minus are quite stable. Okay, so the cation is actually more important here, and that would make the tertiary bromide second, and the primary, honestly, the top one wouldn't react a whole lot fast. It would react,